Good evening, everyone. Tonight we are going to be learning about midpoint and distance formula. When finding midpoint, we have a few options. Option number 1 is using the midpoint formula displayed here. So x1 plus x2 over 2, comma, y1 plus y2 over 2. If you notice, this is the same thing as averaging the 2 points. So if I take the average of the x's and the average of the y's, I would get the same point. We can also use the phrase stack 'em, add 'em, divide by 2. Let's look at an example for each of our options. Find the midpoint of AB, given that A is at 2, 4 and B is at 6, 6. First, we are going to look at using the midpoint formula. So here is my midpoint formula. I've rewritten it for myself. And then I'm going to plug in. So A is my first point, so x1 will be 2 and x2 will be 6. And then y1 will be 4 and y2 will be 6. So when I say 2 plus 6 over 2, I know I'm going to get 4. And then 4 plus 6 over 2, I'm going to get 5. I could also find the average of the x's and the y's. Well, my x's are 2 and 6. So if I take the average of 2 and 6, that's 2 plus 6 over 2, the average will be 4. The average of my y's, 4 and 6, would be 4 plus 6 over 2, so that's 5. So we would still find our midpoint at 4, 5. Our third option is to use the phrase stack 'em, add 'em, divide by 2. So just follow the directions. First thing is stack 'em. So you stack your 2 points one on top of the other. Then you add them. So 2 plus 6 is 8, 4 plus 6 is 10. Then divide by 2. And you find that your midpoint is at 4, 5. Now here's an example for you to try at home. Find the midpoint of RS, where R is at 1, negative 3, and S is at 4, 2. Try 2 of the 3 different methods to see if you get the same answer. We'll check all 3 methods in class. We can also have examples like this. The midpoint of JK is M at 2, 1. One endpoint is J at 1, 4. Find the coordinate of K. So for this we have 2 options. Option number 1 is to plug in the known pieces of the midpoint formula and solve for what you are missing. We know that to find the x in the midpoint formula, it's x1 plus x2 over 2. So in this case, we know that j is at 1, 4, so that would be 1 plus whatever the x value would be for k over 2 equals 2. If I multiply both sides by 2, I find that 1 plus x is equal to 4. So that means that my x value for k is 3. I can do the same thing for y. Since my y value of j is 4, 4 plus y over 2 equals 2. Multiply both sides by 2. So my y value for k is negative 2. So that means the coordinate k is at 3, negative 2. Our second option for this problem is to reverse the phrase that we talked about before. So instead of stack 'em, add 'em, divide by 2, it's going to be multiply by 2, stack 'em, then subtract 'em. And the point we multiply by 2 is going to be our midpoint. So first, I'm going to multiply my midpoint 2, 1 by 2, which gives me 4, 2. And I'm going to stack it on top of the point I know, J, at 1, 4. Then I'm going to subtract those 2 points. So 4 minus 1 is 3, and 2 minus 4 is negative 2. And that is my point K at 3, negative 2. Now, to find the distance between 2 coordinate points, we also have 2 options. Option number 1 is our distance formula. It's the square root of x2 minus x1 squared plus y2 minus y1 squared. Or, if you have a graph, you can use Pythagorean theorem. A squared plus b squared equals c squared. Let's look at this example using the distance formula. Find PQ, where p is at 3, 1 and q is at negative 1, negative 5. So first, I know that p is going to be my x1, y1, and q is going to be my x2, y2. When I plug my pieces into the formula, I get PQ equals the square root of negative 1 minus 3 squared plus negative 5 minus 1 squared. And hopefully you remember that if you have a negative minus a positive, that's the same thing as adding 2 negatives. So I can rewrite this as the square root of negative 1 plus negative 3 squared plus negative 5 plus negative 1 squared, which gives me the square root of negative 4 squared plus negative 6 squared, which becomes the square root of 16 plus 36, which gives you the square root of 52, which can be simplified to 2 root 13. And we're going to learn how to simplify radicals in just a minute. In the case that you're given a graph, you can use Pythagorean theorem to find the distance of PQ. If you draw a line to the right of Q and straight down from P, you can create a right triangle. We can use this right triangle with Pythagorean theorem. A squared plus B squared equals C squared. We know that A and B are our legs and that C will be our hypotenuse PQ. We see in our picture that we have one leg of length 4 and one leg of length 6. So 4 squared plus 6 squared equals PQ squared. So 16 plus 36 equals PQ squared. So 52 equals PQ squared. I need to get PQ by itself, so I'm going to take the square root of PQ squared to cancel out the square. And when I do that, I'm going to do it to both sides. So PQ equals the square root of 52, or 2 square roots of 13, which gives you the same answer as option number 1, the distance formula, did. Now let's discuss simplifying radicals. There are 3 methods for simplifying radicals. Option number 1 is the perfect square method. For this method, you look for the largest perfect square that divides evenly into the number. So below, I've listed the perfect squares between 1 and 25. We know that a perfect square is the square root that reduces to a whole number. So like the square root of 49 is 7, or the square root of 324 is 18. I suggest that you memorize the perfect squares for 1 through 25 as they will pop up on your tests often. Now let's look at 2 examples below. The square root of 24, well, I see that the largest perfect square that goes into that is 4. So it's the same as the square root of 4 times 6. If we have 2 numbers multiplied under a radical, I can separate them into the square root of 4 times the square root of 6. And if we look above, the square root of 4 is 2. So that means 2 square root of 6 would be the simplified form of the square root of 24. Next we have the square root of 72. The largest perfect square that goes into 72 is 36. So the square root of 72 is the same as the square root of 36 times 2. Again, I can separate multiplied things under the radical. So the square root of 36 times the square root of 2, which will reduce down to 6 square roots of 2. Our second option for simplifying radicals is factoring into primes, which we often call the birthday cake method. This means I'm going to keep dividing our number until all we have is primes. So we know our primes are numbers that can only be divided by 1 in itself. So 2, 3, 5, 7, 11, 13, and so on and so on. So we already know from our previous example that the square root of 24 is going to be 2 square roots of 6. So I'm going to take 24 and draw an upside down division sign on it. Well, I know that the smallest prime that goes into 24 is 2, and 24 divided by 2 is going to be 12. And then I'm going to draw another division sign. So then the smallest prime that goes into 12 is also going to be 2. And 12 divided by 2 is 6. And then the smallest prime that goes into 6 is 2. And 6 divided by 2 is 3. And then the smallest prime that goes into 3 is 3 itself. So then 3 divided by 3 is 1. And that's when you know that you stop, once you get 1 on the bottom. Now, once you have it factored into primes, you need to circle your pairs. So I'm going to circle these 2's, and then I have a 2 and a 3. So these 2's are going to get married and move outside the house. So if you notice, they are outside of the radical. And then the 2 and the 3, they're unmarried, they have no pair, so they stay inside the house, and then if they're all the numbers inside the house, we'll multiply together. Now let's try our example with the square root of 72, which we know is going to reduce down to 6 square roots of 2. So I'm going to draw my 72 with my upside down division sign. The smallest prime that goes into 72 is 2, so 72 divided by 2 is 36. And the smallest prime that goes into 36 is 2, so 36 divided by 2 is 18. And then the smallest prime that goes into 18 is 2. 18 divided by 2 is 9, and the smallest prime that goes into 9 is 3. So 9 divided by 3 is 3, and then the smallest prime that goes into 3 is 3, and so then you have 1. So now we are done. Now let's circle our pairs. So we're going to the chapel and we're gonna get married. Alright, so the 2's and the 3's have gotten married. and they are going to move outside the house. So since the 2's and the 3's moved outside the house, I multiply them. So 2 times 3 is 6. And then there's one leftover 2 that stays inside the house, and so it goes under the radical. So your final answer is 6 square roots of 2. Some of you may have noticed that after we divided 72 by 2 the first time, you got 36. And you can, if you see it, skip those steps and just have the 6's get married and move outside of the house. You don't have to factor all the way down to primes if you see a perfect square right away. So this would be a shorter way to do the birthday cake method with the square root of 72. So I know many of you right now are thinking, why do you call it the birthday method? Well, if you take your picture, or your paper I should say, and turn it upside down, then the whole division process looks like a birthday cake with your 1 as your candle. See, look, flame. Isn't that cute? And our last method for simplifying radicals is the factor tree method. This is when we factor the numbers until you hit primes. It's very similar to the birthday cake method, just in a different format. So again, we're going to look at the square root of 24, which we know should reduce to 2 square roots of 6. I'm going to start with 24, and then I'm going to draw 2 lines down from 24, and I'm going to put 2 factors of 24 on each of those lines. So in this case, I'm going to use 4 and 6. Since 4 and 6 are not primes, I'm going to factor them further. So I'm going to factor 4 into 2 and 2, and 6 into 2 and 3. So now 2, 2, 2, and 3 are all primes, and so now go into the chapel and we're gonna get married. All right, so the 2's have gotten married. They're moving outside the house. So here we have our 2 outside the house. And then the 2 and 3 are left inside the house, and so they are going to multiply together and stay inside the house. I'm going to do 72 in 2 different ways. I'm going to show you the short way and the long way. So 72 will have 2 lines coming down from it for the 2. So I'm going to factor 72 into 8 and 9, and I'm also going to factor 72 into 2 and 36. Since 8, 9, and 36 are not primes, I'm going to factor them further. So I'm going to factor 8 into 4 and 2, and 9 into 3 and 3. 2 is prime, so it stays, and then 36 factors into 6 and 6. And then I could factor 6 and 6 further, but since I've already found a set of a pair, I can go ahead and circle them, and they can get married and move out of the house. And so then on the right, I would be done because there are my 6's, they've moved out, my 2 is still left in the house, and 6 square roots of 2 is my simplified form. On my left factor tree, I would have to continue factoring and factor the 4 into 2 and 2, and then I could marry these 2's and these 3's. They would multiply and move outside the house together and become 6, and then the 1, 2 left over would stay inside the house. So we still come out to 6 square roots of 2. That is everything I have for you tonight. See you in class.